Assalamualaikum warahmatullahi wabarakatuh. We are from Group 3 of Introduction to Real Analysis 1. We will going to explain the result of our discussion about the completeness property of real number. First, we are going to introduce our member of group. My name is Fariza Rohmah, and my friend is Kirana Dara. And first is 2.3.1 definition is let S be a non-empty subset of R. And A, the set S is said to be bounded above if there exists a number U element real number such that S less than equal U for all S element S. Each such number U is called an upper bound of S. In B, the set S is said to be bounded below if there exists a number W element real number such that W less than equal to S for all S element S. Each such number W is called a lower bound of S. And C, a set is said to be bounded if it is both bounded above and bounded below. A set is said to be unbounded if it is not bounded. For example, the set S, there are x element R, x less than 2 is bounded above the number 2, and any number larger than 2 is an upper bound of S. The set has no lower bound, so that the set is not bounded below. Thus, it is unbounded even though it is bounded above. If a set has one upper bound, then it has infinitely many upper bounds. Because if U is an upper bound of S, then the numbers U plus 1, U plus 2, and etc. are also upper bounds of S. This similar observation is valid for lower bound. In the set of upper bound of S and the set of lower bound of S, we single out their least and greatest element, respectively, for special attention in the following definition. And like the figure 2.3.1. Next is 2.3.2 definition. Let S be a non-empty subset of R. In A, if S is bounded above, then a number U is said to be a supremum or a least upper bound of S if it satisfies the condition. First, U is an upper bound of S, and second, if V is any upper bound of S, then U less than equal V. And B, if S is bounded below, then a number W is said to be an infimum or a greatest lower bound of S. If it satisfies the condition. First, W is a lower bound of S, and second, if T is any lower bound of S, then T less than equal to W. Next, there are four possibilities for a non-empty subset S of real number. It can first have both a supremum and an infimum. Second, have a supremum but no infimum. Third, have an infimum but no supremum. And fourth, have neither a supremum nor an infimum. The statement about an upper bound U of set S are equivalent if phi is any upper bound of S, then U less than equal to phi. And if Z less than U, then Z is not an upper bound of S. Next, if Z less than U, then there exists SZ element S such that Z less than SZ. Next, if epsilon greater than 0, then there exists as epsilon element S such that U minus epsilon less than S epsilon. Next will be explained by Kirana Dara.
2.3.3 lemma. A number U is the supremum of a non-empty subset S of real number if and only if U satisfies the conditions: first, S less than or equal U for all S element of S. Second, if phi less than U, then there exists S accent element S such that phi less than S accent. Next, 2.3.45. An upper bound U of a non-empty set S in real number is the supremum of S if and only if for every epsilon greater than 0, there exists an S epsilon element S such that U minus epsilon less than S epsilon. You can see in the figure. And the proof, if U is an upper bound of S that satisfies the stated condition as defined, U minus O, there exists S epsilon element S such that phi equal to U minus epsilon less than S epsilon. Therefore, phi is not an upper bound of S, and we conclude that U equal to sub S. Conversely, suppose that U equal to sub S and let epsilon greater than 0, since U minus epsilon less than U, then U minus epsilon is not an upper bound of S. Therefore, some element S epsilon of S must be greater than U minus epsilon, that is U minus epsilon less than S epsilon. For example, when if a non-empty set S1 has a finite number of elements, then it can be shown that S1 has a largest element U and element W. Then U equals and W equal to inf S1. The set S2 as defined less than or equal 1 clearly an S set such that phi less than S accent. Therefore, phi is not an upper bound of S2. And since phi is an arbitrary number, phi less than 1, we conclude that sub S2 is equal to 1. It is similarly shown that inf S2 equal to 0. Note that both the supremum and the infimum of S2 are contained in S2. The set S3 as defined X when 0 less than X less than 1 clearly has 1 for an upper bound. Using the same argument as given in 2, we see that sub 3 is equal to 1. In this case, the set S3 does not contain its supremum. Similarly, if S3 equal to 0, 0 is not contained in S3. The complex subset test of real numbers, the number. The completeness property of real number. The completeness pair theorem regarding non-empty subset test of the real numbers that are bounded below exists and proven below. Theorem 1. Every non-empty subset S of the real numbers that is bounded below has an infimum in the real number. Proof. Let S be a non-empty subset of real numbers that is bounded below. Then there exists a lower bound M element real number such that M less than equal S for every S element S. Define the set T by T equal to minus S as element of S. Then observe that minus F less than or equal minus M for every minus S element of T. So T is a non-empty subset of real numbers that is bounded above. When the completeness property of real numbers, we had that T has a supremum E, then minus S less than equal X for every minus S element T, and if Y is any other upper bound of V, then X less than or equal Y. So observe that minus X less than or equal S for every S element S, and if Y is any other lower bound of S, then Y less than or equal minus X. So if S equal to minus X, in either words, S has an infimum in real number. The relationship between supremums and infimums. Let F be an ordered field with the least upper bound property, and let A subset of F be non-empty and bounded below, and define B equal to B element of F when B is a lower bound of A, shown that sub B is equal to inf A. Proof. First of all, note that A is non-empty, and therefore there exists some A element A which satisfies B less than or equal A for all B element B. Because its B is a lower bound of A, then B is bounded above by A. Hence, because F has the least upper bound property, B has a supremum. Let X equal to sub B, we just need to show that X satisfies axiom I1 and I2 of the definition of the infimum. I1, give any A element A, B less than equal A for all B element B, therefore A is an upper bound for B by S2. Since sub B is the least upper bound of B, we have the sub B less than or equal A. Since A element A was arbitrary, it follows that sub B less than equal A for all A element A. Hence, sub B is a lower bound of for A. I2, given any other lower bound L for A, note that by definition of B, L element B, therefore L less than equal sub B, hence sub B is the greatest lower bound of A. Hence, X is the infimum of A as desired. Then, it's all from our presentation. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.